Let's say we have, in general, our agonist, and we're going to represent agonist here in black, okay? So here's our. What's up, Ninja Nerds? In this video today, we are going to be talking about pharmacodynamics. If you guys really want to understand this, I truly strongly urge you guys go down in the description box below. We'll have a link to our website. On our website, we'll have some awesome notes, but even better, some illustrations that you guys can follow along with me as we go through this lecture. So go check that out. Also, please, if you guys like this video, you benefit from it, it makes sense, it helps you, please support us, and the best way you can do this is by hitting that like button, commenting down in the comment section, and please also subscribe. All right, let's talk about pharmacodynamics. When we talk about pharmacodynamics, it's basically a very interesting concept that we're going to pick up from pharmacokinetics. So if you guys remember from pharmacokinetics, really basic, the ADME, the absorption of the drug, the distribution of the drug, the metabolism of the drug, and the excretion of the drug were all a part of the pharmacokinetics, where you take a drug, and we said in a perfect world, let's say that we take it orally, PO, moves through the gastrointestinal tract, has to be absorbed, so it has to cross cell membranes. When it crosses cell membranes to get into the blood, it goes into the hepatic portal system. The hepatic portal system will then take this medication to the liver. The liver will always, if it goes via the oral route, will get some piece of that drug where it can activate or break down some of the actual drug. So it'll have what's called first pass effect or first pass metabolism. So then what it'll do is some of that drug, it may metabolize, and then the other remaining portions it'll put into the systemic circulation. From there, we know once the drug goes, it'll actually distribute throughout the actual vasculature and into the tissues where it can go and exert its effect. This here is where we're going to see the pharmacodynamic effect. But if you guys remember, finishing off the pharmacokinetics, after a drug is done performing its particular function, or it's moving through the circulation, it can be taken to the kidneys, where it can be excreted, or it can be taken to the liver, where it can be metabolized and also excreted. And these are the primary organs of clearance of the drug. Now, whenever the drug gets to the actual tissues, what we can see is what the drug does to the actual body, whereas pharmacokinetics is like, what the body is actually doing to the drug, if you will. So now we have to see, what does this drug actually do to the body, particularly the cellular component of our tissues, our organs subsequently. So if we take and we actually look and zoom in at this drug interaction here, we're going to look at one of these particular cells. So here's our drug. In order for a drug to be able to bind to a cell and produce a particular cellular response, it needs to be able to act on a receptor. Right? So there needs to be a receptor that the drug can actually bind to. Once it binds to that receptor, it'll then produce a particular cascade of events intracellularly that activate the cell or inhibit the cell and cause it to produce the appropriate cellular response. So some drugs are working to inhibit the cells, some drugs are working to stimulate the cell. Either way, that is the cellular response. In order for the drug to do that, it has to bind either to a extracellular receptor, we'll put EC receptor, and then via second messenger systems work to be able to stimulate second messengers to produce the cellular response, or the drug has to be able to move into the cell and bind onto a intracellular receptor, where it'll then again produce a cellular response via a specific cascade of events. What we have to understand now is if we take this drug and have it bind onto extracellular receptors, what are the different types of extracellular receptors and why are they different? What are some examples of drugs that act with different types of receptors? And then we talk about the intracellular receptors and what kind of drugs particularly interact that way. We're not going to go down the crazy rabbit hole of signal transduction and intracellular receptor pathways. We talk about that in cellular biology, but it's just enough for us to understand the basic concept here. And the last thing we'll do is we'll talk about something called desensitization, also known as tachyphylaxis and tolerance, with respect to drug receptor interactions. All right, so let's come and now talk about when we have a drug interacting with a receptor, let's say an extracellular receptor, what happens? All right, so we have different types of extracellular receptors. First one that I want you guys to remember is drugs can actually bind onto extracellular receptors that are for what's called a ligand-gated ion channel. It's actually pretty straightforward. Let's say here I have a neuron. On this neuron, I have these particular channels, if you will, that are supposed to allow for maybe particular ions, maybe positive ions to flow in, maybe negative ions to flow in, maybe positive ions to flow out. Either way, it's some kind of concept like that. There's a little gate, if you will, that's basically controlling the entry of drugs. So these ions are not going to be able to allow for these, this gate is blocking these ions from moving into the actual cell. But if I give a particular drug that wants to bind into this little pocket here, that's a part of the ligand-gated ion channel. And once it binds onto that pocket, it lifts the gate open. And now this gate that was completely closed is open, and there's an opportunity for the particular ions to easily flow in or out of this neuron. And now, this is actually a really cool concept. For example, let me tell you an example of a particular drug here. Let's say I have a drug such as lorazepam. So lorazepam is really interesting because lorazepam acts on what's called GABA-A receptors. So it'll work on what's called GABA-A receptors. Now GABA-A receptors are ligand-gated ion channels. So let's pretend this black dot here is GABA. When GABA binds onto these channels are generally closed. We don't want them to be open. But when GABA binds to it, what it'll do is it'll open up the channel and allow for negatively charged chloride ions to easily flow into the actual neuron. And as these chloride ions inflow into the neuron, it makes the cell super negative. And it basically hyperpolarizes it and decreases action potentials. You want to know why this is interesting? We can give lorazepam in situations where you want to decrease the activity of neurons. You know where that would be a very important situation? Seizures. So it may be able to work to inhibit or decrease seizure activity. So that's kind of one example of how drugs can work at the receptor and produce a cellular response, is they bind onto a ligand-gated ion channel, either open that channel, close that channel, and then depending upon what kind of channel they bind onto will determine which kind of